All right, my friends. Last time we were talking about higher degree functions. We talked about end behavior, possibilities for real and imaginary roots. We had an important theorem called the factor theorem, and this was for integers. So we used like 2. If 2 is a root, then x minus 2 is a factor. And then we used synthetic division to factor out the factors we knew, reducing that degree down to a quadratic where we could factor and find the rest, the other 2 zeros. We're going to keep talking about higher degree functions and have a little bit of a twist on that factor theorem. First, just to get this out of the way, this video is about some material that's kind of out of date, honestly. These are questions you could answer with a graphing calculator or a smartphone pretty quickly, but we're going to do them because math's awesome, and we can pretend it was 100 years ago. First rule, possible rational roots. The rational root theorem says the only possibilities, all right, we have a fourth degree function, so we have four. We could have up to 4 real roots. And a rational just means, it's not a never-ending decimal. It's something like 3/4. It can be expressed as a simple fraction. All possibilities for real rational roots are some factor of the constant, in this case, -15, and the negative doesn't really matter here, divided by some factor of 4. All right, that's what it means. I just tried to express it as simply as I could. A factor of the constant divided by a factor of the leading coefficient. So you'll get a question that might say, list all possible rational roots. So start by just, on a big fraction bar, list all the factors of 15, including the negatives. Plus or minus 15, plus or minus 5, 3, and 1. And then below that, list all possible factors of 4, 2, and 1. So the answer to that question, list all possible, is going to be a big long list of plus or minus numbers that are some combination of one of these on top divided by one of these on the bottom. So I could have, I'll just kind of work through it in order, plus or minus 15/4. So that's a rational number, right? It is a possibility that this quartic equation, its graph goes through -15/4 or +15/4. Okay, so if it's not in this list I'm making, it's not even a possibility. And imagine if you lived a million years ago like I did and you weren't able to just graph this thing and look, you would want to know this to narrow down your possibilities. So anyway, we'd have plus or minus 15/2, plus or minus 15/1, or just 15, plus or minus 5/4, plus or minus 5/2, plus or minus 5/1, which is plus or minus 5. Keep going, big long list. Usually these, depending on the nature of the numbers, they could be lengthy. 3/4, 3/2, 3. And then we have 1/4, 1/2, and 1. Okay, so all of those are possible rational roots. So if I'm not able to look at a graph on a calculator and I want to know the roots of this, then I'm going to have to start guess and checking my way through this list. And when I guess and check, I'm going to divide out the associated factor and see, do I get a remainder of 0 or don't I get a remainder of 0? Before we start dividing out, you need to learn this next rule. That factor theorem in the last video that said if 2 is a root, x minus 2 is a factor, sadly that does not work for all rational roots, okay? Before we start finding specific ones, here's the rule. If b over a is a root, then ax minus b is a factor. So what that means for us is, let's say 2/3, for example. Before I get to this example, I'm going to move down and have another example. If 2/3 is a root, meaning the graph goes through 2/3 on the x-axis, I cannot say x minus 2/3 is a factor. I say 3x minus 2 is a factor. All right, it's very tempting to just say x minus 2/3 because that's what we did if it was a whole number. It is not x minus 2/3. If you think about it, 2/3 makes x minus 2/3 into 0, but 2/3 also makes this one into 0. And for reasons beyond the time we have in this video, we go with the blue underlined one, 3x minus 2. Okay, so what we need to do with these possible fractional solutions is write the factor, divide it out of the fourth degree polynomial, and see if we get a remainder of 0. Another sad event here is that we can't use synthetic division. We're going to have to use polynomial long division. So let's try 3/2. We'll try positive 3/2 just for kicks. If positive 3/2 is a root, then the factor would be 2x minus 3, okay? Because think about it, 3/2 makes that 0. So if I want to check and see a million years ago if 2x minus 3 goes into this polynomial, I'm going to have to do polynomial long division. Okay, and that's going to work a lot like 4th grade long division. And that's going to look like this. Okay, the first question I need to ask myself, what do you need to multiply 2x by to get 4x to the 4th? And the answer is 2x to the 3rd. I'm going to write that above the cubic term in that's underneath. Now I'm going to multiply this. I'm going to distribute it to both terms and write this underneath. So 2x cubed times 2x is 4x to the 4th. These two should match up perfectly every time, otherwise you chose the wrong answer up top. My next term is minus 6x cubed. I need to subtract that from the line above. Always getting 0 here because they have to match perfectly. Negative 12x cubed minus negative 12x cubed is plus, 6. That's negative 12 plus 6, which is negative 6x cubed. And then much like 4th grade long division, we're going to bring down the 25x squared for our next cycle through. So what do I need to multiply 2x by to get negative 6x cubed? And the answer is negative 3x squared. You can see how when we did synthetic, we took all the x's and the exponents out of the way, just dealt with the coefficients. It doesn't work so simply with a rational root like 3/2. Okay, so now I'm going to distribute. I get negative 6x cubed. Matches up perfectly with the term above it, plus 9x squared. Subtract all of that. So I get 25 minus 9, which I'm pretty confident is 16x squared. Drop the 14x. I need to multiply 2x. Notice when I'm asking myself, what do I need to multiply by? I don't care about the minus 3. I just care about the 2x. I need to multiply 2x by 8x to get 16x squared. I'm going to put that 8x up top. 16x squared minus 24x gives me, let's see, negative 14 plus 24 gives me 10x. I drop down the negative 15, and at this point I can tell that this is going to go in evenly, because what do I need to multiply 2x minus 3 by? I need to multiply it by 5. And then I get 10x minus 15. Sorry, I'm out of space down here. Subtract and get 0. So there's that remainder of 0 that I'm looking for to confirm that this actually is a factor. Now, I obviously knew the answer going in because I had this huge list and I chose one that happened to work. If you don't get a remainder of 0, that means the one you searched for is not truly a factor and you need to try another one. And then you try another one, and then the cubic that you get left over, you factor that one out and see what you get. So far, on the way to factoring this thing and finding the zeros, I have figured out this much. Let me get rid of my earlier info. What I know at this point is that 2x minus 3 is a linear factor, and the cubic factor that's left over is 2x cubed minus 3x squared plus 8x plus 5. So I still have a cubic left to deal with. All right, so the factor that will go into that cubic is also one on this list. So again, I can start guessing, checking, doing long division each time. For the sake of time, I'm going to look at a picture of it and just show you how that picture would be connected. Here are my zeros. I have 1.5. That's the 3/2. I also have a real zero at negative 1/2. All right, so that's 2x plus 1 as the other one that I know is going to work. 2x plus 1 should work because negative 1/2 would correspond to 2x plus 1. So what I need to do now is divide 2x plus 1 into the remaining cubic, and I should see 0. I would not know that I'm going to see a 0 remainder, except that I have a picture, so I cheated my way to knowing that, but I'm going to get a remainder of 0. So since this link's getting a little long, I want you to pause, work this out, and I'm going to jump into the future in about 5 seconds and have the answer ready. So pause and work it out, and then come back and see the answer. All right, so here we are, a minute or two into the future. Make sure that you agree with this long division. The common mistakes are going to happen at places like this. See if you can guess what answer I'm normally going to get here, or a lot of times. I'm going to get a 6x right there instead of a 10. You can see why. I need to subtract all of that. Subtracting a negative, I add. That's just something you can do if you're moving too quickly. So let's get back to the original question. I'm trying to factor and find the zeros. So my original polynomial is going to factor to 2x minus 3, 2x plus 1, and then the quadratic that's left over is x squared minus 2x plus 5. And that's a quadratic that, again, may or may not factor. And again, I know that it's not because, remember this, if that quadratic were going to factor, then that would mean 2 more nice, neat, rational roots that would be showing up on this graph. And since I only see 2, I know it's not going to factor. I also know that there are no factors of 5 that add up to negative 2, so it wouldn't take me long to try to factor that and realize that it wouldn't, but the picture confirms that it should not. So the last thing I want to do to find my last 2 zeros is put this quadratic into the quadratic formula and see what I get. I'm going to pause again, jump to the future. So pause your video, do the quadratic formula, and I'll be right back with you. All right, I'm back. So I hope that you paused and tried that on your own. If not, at the very least, copy it down and make sure you understand. It's been a long process, but back up here, the original question was to find all zeros. So I have the 3/2, I have the negative 1/2, those I either see from my picture I was given in the equation, or if it's a long time ago, I've plotted my way through this big list of all possibilities until I found the ones that worked. But one way or the other, I found that those are my 2 zeros. My other 2 are 1 plus or minus 2i. Which again, notice that imaginary / complex answers, they always come in conjugate pairs. You're not going to have 1 plus 2i without 1 minus 2i. All right, so just remember the most common thing. Do not see a 0 at 3/2 and say x minus 3/2. Convert that to 2x minus 3. And that's going to do it for this one. I hope you've enjoyed the rational root theorem. Young out.